Hello world and welcome to Fun with Electronic Soup with me, your host, John Whitmore. Episode 2. In the first episode I created 3D printed a little jig so I could use a solder stencil. I've never used a solder stencil before, so I'm trying to test out now. I'm going to test that everything is soldered up correctly. As you can see, I made my first mistake, which is this green wire. Basically, when I moved to the Mark III, I replaced my DC-DC converter, switch mode power supply buck chip. And my mistake was that I designed this standalone as another circuit and labeled the output voltage V out or something. But in this, on the cinnamonBun, the 5-volt rail is labeled as 5V, of course. So, yeah, there was the schoolboy error. So the simplest thing to do was basically hand solder it to the 5-volt rail, and the handiest place to get it was this chip, which is the 3V3 DC-DC converter. So it takes the 5 volts in and creates the 3V3 rail for the actual PIC is running at 3V3. Which is important to remember that this is a 3V3 device, and very few, if any, of its pins are capable of handling 5 volts. But there is a 5-volt rail on the board, as well as a 12. There's 4 rows of I/O, the 4 rows of I/O, and they're all the same in terms of, like, these female pins are power. So each line has got ground, 3V3, 5 volts and 12 volts. Now the 12 volts is coming in on the center pin here. It's a nominal 12 volts because I'm basically designing this for the automotive industry, and while a lead acid battery is 12 volts, a nominal 12 volts, when a car is charging, when the alternator is charging that battery, that voltage will go up to 14.5 or there and thereabouts. So, or potentially up to 14.5. So you have access to that 12 volt rail if you put an expansion on top. So each one of these, ground 3V3, 5 volts 12, ground 3V3, 5 volts 12, all 4 are the same in that respect. The actual male pins, the top, as we're looking at it here now, is port D. It's an 8-bit port. Port E is the next one down, an 8-bit port. And the lower 16 are port B, which is a 16-bit analog port. So this is pin 0 through to 7, and then 8 starts over here back to 15. So that's 0 through and back to 15. So I wanted to, because I've never used a solder stencil before and used that mechanism for soldering, I decided I'd design and order up a test PCB. So I've got this little board, which is basically just a very simple, it has a lead for each of the rails on each of the various lines. So 3V3, 5 volts and 12, 3V3, 5 volts and 12, and then leads for each row of the I/O. I shouldn't have bothered putting the support pillar holes there, but don't know what I was thinking. It hardly makes sense in a test board. So my other thing is, all these pins, both the power and the I/O, marry up to a 2.54 millimeter spacing. So when they line up on the top, they line up on the bottom, sort of thing. So all 32 I/O pins, as well as all the power, will line up there, so you have access to all these if you want to use a Vero board. My slight omission is that these 3 pins, which we'll come to at a later date, and the in-circuit serial programming interface, I didn't actually have those lined up on the 2.54 millimeter grid. So I think when I do version 4 of Mark IV of this board, I'll correct that, and I think it probably makes sense to have everything as on that grid. So now, to test this out, we just basically want to create a project in MPLAB-X. So create a new project. The default is a standalone, which is what we want, a standalone project, and we want, it's a DS-PIC33 EP256MU806 top on the list there. So create that. I'm going to use the PIC Kit 3, which I have connected, and I'm going to use the XC16 compiler. I have no optimizations, I have no license, I'm just using the free compiler as the minute, because I think that's more accessible if people are interested in following along. I don't want to preclude people. And as you can see, this interface isn't the best, but I'll try and call this soldered project is solder test. As you can see, it's half lines. I assume that's just because I'm using Linux. So very quickly, we don't need that. We need a new C source file, call it main. And the first thing we do is include xc.h. That's a catch-all header file that will basically, the build, the make files will work out what processor, what microcontroller you're using, and include the correct header file for your project. So as I say, we've got 32 I/O pins here, but I don't want to send 20 milliamps to all 32 at the same time. So we'll do a row. We'll do the low order of port B, then the high order byte of port B, and then port E and port D, and a delay in between. So we'll do it one line at a time with a delay. So I shall define a delay and try and spell it correctly, and we'll just make it a for loop. Make it quite big, and in the body of the for loop we'll just use the no-op function so that it's doing nothing. So then microchip's main prefers if you have a return, so we'll call it an int and return 0. Not that it means anything in an embedded system. And my delay function there, or my delay macro, used a variable called delay, so we'll have to create that. And now we're starting on port B, and as I've said, that's an analog port. Basically any pin that is potentially an analog pin, when the microcontroller powers up, will be configured as an analog pin. So we want to set all pins digital and outputs. So to set them as digital, digital, we need the analog select for port B and set that to 0. And then for output pins, we need the tri-state and set that to 0. 0 is output, 1's input. And then we need the latch for port B, and we'll set the low order 8 bits to 1. Delay, and then we'll turn off the low order and turn on the high order, and delay again. So that should be port B. Illuminate the lower 8 bits, delay, illuminate the high 8 bits and delay. So then we're going to go to the next one, which is port E. So exactly the same again. We want the analog select for port E. We now need the tri-state for port E, all bits output, and then we'll set the latch and delay. And then finally, same again, port D. So the analog select for D, tri-state for D, and the latch for D. So we'll illuminate those 8 pins and delay again. And at the end of delay, we want to turn those pins off, which I didn't do above for port E. So turn them on, and I didn't do it. I didn't do it for port B. Right, so on, off, on, off. Check that. That seems about right. So we'll put all this in a while loop. An infinite loop, the while one, and we'll indent this. As you can see, MPLAB-X isn't the best at indenting comments intelligently, but we'll leave it. It's just a... Actually, I prefer to work in just editing Emacs. The one thing that MPLAB-X is needed for is that to program with the PicKit 3, you actually need to use the MPLAB-X. We'll get to that now. So that builds, if I connect up my power, the power is this 5 volt, the 5 pin here. Like I say, 12 volts in the middle and the ground on the outsides. So you can't mix up. If you get this either way, it's still going to work. So the other 2 pins are CAN high and CAN low. They're not reversible, so when we get to CAN, if you plug it in the wrong way, you're going to mess up your network. So connect the PicKit 3 and go back and compile, build, install that, program that into the flash. And that's us. So now if I remove that and connect up my connect up my test board, and hopefully when I power up, so we've got 4 3v3 lights on that rail, we've got 4 5 volt, and we've got 4 12 volts. So all the voltage rails are present and correct. We're missing port pin RB0. So that we've got 1 out of there. We do have all of the high order port B. We seem to have all of port E, and we've all of port D. So our solder stencil soldered up everything except 1 pin RB0, which I have to check now and resolder. So that's it, a test board, a bit of code, and quite happy with my solder stencil. Thanks a million for watching. Hopefully the next episode will do something a little bit more constructive. Thanks again.